this morning. This webinar will be recorded so that if any of your colleagues are not able to attend for whatever reason, it should be available as early as tomorrow for viewing in the future. This webinar is going to be anywhere from 30 to 35 minutes long. We'll have plenty of time for questions at the end of it. I am going to mute everyone's line, and this is going to be a webinar that focuses on using high accuracy GNSS mapping systems for wastewater management. So before we get into the webinar itself, I would like to give you a little bit of information about the history of the Trimble centimeter mapping systems. It was about 2 years ago that Trimble decided to release an option for their Geo XH6000, enabling people to upgrade to a 1 centimeter mapping system. And at the time, we really weren't sure who this would appeal to, because obviously survey mapping system or survey centimeter systems have been around for a long time. And so we began to discover over time that people that have been very interested in a product like this, because they needed to get very good accuracy, were people like water districts, public utility districts, public works departments, and anyone else who needed to get high vertical accuracy in addition to typical horizontal accuracy. So that's how all this started, and so with that, let's begin the webinar. A little bit about our company for just a moment. Electronic Data Solutions has been around for 26 years. We offer a wide variety of hardware and software, and everything that we sell comes complete with technical support, training, and repair services. We also conduct formal classes for those of you that would like to get more in-depth information about whatever product you procure from us. Our home office is in Jerome, Idaho, which is in south central Idaho, and we currently have 26 employees occupying 8 different offices in 6 different western states. And that little graphic in the lower right-hand corner of the slide, you can see where we are located. So the Trimble Geo 7X centimeter kit was introduced about 15 or 16 months ago, a little over a year, and it was really the first system that was sold primarily as a centimeter mapping system from Trimble Navigation. It includes a modular laser rangefinder, which allows you to take remote point features. It does include a 3.5G cellular modem, and this modem is basically a universal modem that can be activated on a GSM system like AT&T or a CDMA system like Verizon. This particular unit has doubled the data storage over previous models, up to 4 gigabytes of onboard data storage. It also supports up to a 32 gigabyte SD card, so that if you need more storage than that, you can certainly have up to 36 gigabytes of storage. This unit has a 1 gigahertz processor, which is substantially faster than the previous Geo 6000 model. And it does include the Zephyr Model 2 GNSS antenna, which is a survey-grade antenna, enabling the user to get 1 centimeter horizontal. A little bit about the Geo 7X. It's a multi-constellation receiver. It picks up 4 different position constellations of satellites, which of course are GPS. The GLONASS is the Russian system. It picks up the Galileo system, which is European, and then finally the Compass, or the BeiDou system, which is Chinese. In addition to those 4 positioning constellations, it also picks up WASS, which in this country provides for some real-time corrections, and also the QZSS system in Japan, which does the same thing over Japan. One of the big improvements for this particular unit is it does have SBAS, but it has something called SBAS Plus. And for those of you that had previous models using SBAS, you probably remember that when you picked up the correction signal from one of those equatorial satellites, it would make all the Russian satellites disappear on the sky plot. Well, SBAS Plus allows the WASS signal to apply corrections to all the satellites in view, so you don't lose any satellites graphically off your sky plot. So it's quite an improvement. The Geo 7X has several sensors. It's got the built-in laser rangefinder, which provides distance, the inclinometer, which will provide vertical angle, and the compass, which of course provides horizontal angle. It's a very easy to use sensor calibration utility built right into the system itself. And the laser rangefinder with the compass and inclinometer provides the ability for the user to collect several different types of measurements. Not just offsetting a point feature, but you can do a multiple offset to a point feature. You can also calculate the heights of objects, and you can also calculate what we refer to as missing line. Missing line example is you want to get a distance between this pole and that pole. You can shoot one and then shoot the other, and it will give you the distance between those two remote points in addition to the basis of bearing. So pretty sophisticated. We should talk a little bit about the accuracy, because this, of course, is going to have a direct effect on the final resting place of that offset point feature and how accurate it is. So the laser rangefinder has a distance accuracy of plus or minus 5 centimeters, or excuse me, 5 centimeters, which is less than 2 inches. It'll shoot out to 400 feet to any object, or out to 650 feet with a reflector. So a reflector would be considered reflective tape on a vest, a license plate, a stop sign, a piece of survey glass. The inclinometer has a vertical angular error of 0.5 degrees, and the compass, providing horizontal angle, has an error of 1.5 degrees. So because of all these errors, we strongly recommend that you keep your shots as short as possible to maintain as high an accuracy as you can. The laser aiming is pretty simple. It actually uses the built-in 5-megapixel camera as the sighting device, so that when you look at the screen, the entire screen is dedicated as your sighting device, and you can make sure that you're hitting the right object. If you're pointing the laser at a reflective surface, you can also see the red dot. And of course, there's 2 different ways then that assist the user in making sure that you're hitting the right feature. The physical button on the screen, or the physical button, excuse me, is what takes the measurement. And you can see that little button in the middle there. This graphic actually shows a Geo XH, not the Geo 7, but the people who provide these graphics haven't put the Geo 7 online yet. So that little button that looks like a camera is the one that actually takes the measurement. If you hit the wrong object, you can zero out that measurement. Or if you like that measurement, then you can basically hit the check mark in the lower right-hand corner of the screen, which then saves that measurement and applies the offset to the TerraSync software. So why are we talking about centimeter in the realm of mapping and GIS? Well, basically, centimeter traditionally, as you know, has been purely in the realm of surveyors. But because of demand and because of the possibility, and the technology has improved to the point, and the prices have come down to the point where now it's possible to go out there and collect very high accuracy data for GIS. So very common for this need to be in water wastewater projects, irrigation projects, utility mapping of all types, the ability to determine land boundaries to a high degree of accuracy, and of course maybe targeting for LiDAR projects, and many other applications. This product will produce 1 centimeter horizontal, 2 to 3 centimeters vertical. So the vertical is not quite as good, but keep in mind that 2.5 centimeters equals 1 inch, so you're still talking about incredibly good accuracy. In today's world, a sophisticated RTK survey system will cost the user around $25,000. This system will cost the user $16,500 or less, depending on purchasing contracts or other arrangements. And this level of accuracy can be achieved either in real time or by post-processing back in the office. And we'll talk about those details as well. So we have a polling question for you. So I'm going to launch the first poll. And the first poll says, how important is it to you to achieve 2 to 3 centimeter elevations? So I'm going to put that on the screen. And when it appears on your computer screen, take the time and just answer those questions. Well, that's great. It didn't take people very long to actually log in their votes. Some of you have said tremendously, and the other half have said somewhat often, which is great. All right, well, that kind of tells me that this you guys are in the right place, and this is probably the right webinar. So thanks for being here once again. Okay, so let's continue. I'm going to make sure that you can actually see my screen still. We've got some slides here that I think you'll be very interested in. We decided to put this webinar together and occupy it or populate it with some actually existing users. I think this would probably help everybody understand that we actually do have people out there using this for various reasons. The first existing user, and probably our oldest user, I think they purchased this system probably almost 18 months or 20 months ago, is the City of Auburn, Washington, and their Public Works Department. The history behind this particular user was that they also have a survey department in this agency, and the Public Works Department had been going to the survey department to ask if they could borrow their expertise to help them get elevations on the top of culverts. And because the survey department was quite busy, they had plenty of work in front of them, they had a hard time breaking away from their normal duties and helping Public Works get these elevations. So when it came time for them to put out a contract to purchase a system, when the survey department discovered that Trimble actually offered a 1 centimeter mapping system, they strongly encouraged Public Works to get that particular system. Obviously, it freed the surveyors up from having to break away from their regular duties, and it put the ability in the hands of the Public Works people directly to be able to get these high accuracy elevations. So they're using this to get locations of manholes and elevations. They're using it to get the location of storm sewers, and in addition, of course, to get those elevations on the top of culverts. So they now have a little more control over the data that they're managing. They can collect their own data, and because of the success of the first system, about a year ago they bought a second system, and they currently have 2 of these in use. Now, what's interesting about this particular agency is they are a member, a co-op member of the WSRN, which is the Washington State Real-Time Network. And because they're a co-op member, which means they supplied one of the many base stations that are comprised in this system, they're able to get the data stream that provides them with real-time accuracy in the field free of charge. So what they do, they log into the IP address of the server while they're in the field, and they do this through a cellular modem. That's why it's important to have a built-in modem in these devices. They type in their login and their identity. They're able to then receive real-time corrections in the field so they can walk around anywhere in their jurisdiction and get a centimeter of accuracy. Okay, our next user is the Lake Haven Utility District. They're a utility district up in Federal Way, Washington. They were very interested. Their history is they had a TopCon system, probably 7 or 8 years old, and they decided to buy a new system, and so they decided to look at Trimble for the first time, and they heard a lot of good things about it, and so they had a couple of demos. They actually rented the system for a couple of weeks to make sure that before they made a purchasing decision, they actually were buying the right thing, and they were very happy with what they got. So they're now using a Geo 7X centimeter edition to get locations of water valves and hydrants. What's unique about this particular agency, they're using it to update existing features which formerly were digitized in GIS. And of course what this means is that about 10 years ago someone stood in front of a computer screen and used aerial photogrammetry to determine where some of these hydrants and manholes were located. And of course, because of some of the errors built into the aerial photograph itself, they didn't really pick precisely where these objects were. So what these guys are doing is they're loading the layers into TerraSync software. They can see the hydrants and manholes on the screen. They use GPS to navigate back to that location. and then they actually are able to update or physically move the incorrectly digitized feature to its correct location down to 1 to 2 centimeters of accuracy. So they're collecting new features in addition to updating existing features. And once again, they are using that Washington State real-time network in order to get real-time corrections. Our next user is the U.S. Army Corps of Engineers. These guys are located at the McNary Dam, which is in Burbank, Washington. These guys happen to be about 15 miles east of Tri-Cities, which is in southeastern Washington, very close to the Oregon border. They decided to get a centimeter unit to map locations of docks, trails, trees, shrubs, stairs leading from a property owner down to the river, property corners, in addition to landowner boundaries. So they decided that they didn't need centimeter accuracy for all these features, obviously, because a dock is a large thing, but they also knew that during those times when they needed that high accuracy, they wanted to have access to it. So this is interesting for these guys because they're not receiving real-time corrections. So in the field, they're not seeing on the screen that they're obtaining 1 centimeter of accuracy. However, TerraSync software, which is the software that they're using to collect this data, has the ability to display your estimated post-processed accuracy even though you're still in the field. So what this means is they're able to determine that they have been at this point long enough and they have observed at this location long enough so that when they do post-process their data back in the office, they'll get a given level of accuracy. So it's a pretty sophisticated system. So if they need to get real-time accuracy, they do have to log into a single base, which is the closest base station to them, but otherwise they're basically collecting raw data and they're applying corrections back in the office. Our fourth and final existing user, our most recent user, is the City of Lake Oswego, Oregon Public Works Department. Lake Oswego is just south of the city of Portland. They're kind of considered the Beverly Hills of Portland. So because of the wealth that occupy this particular city, they have a fairly high tax base. And even though they do have survey systems, they were intrigued by the concept of getting a much less expensive mapping system, which would be very friendly to GIS and still provide them with the necessary accuracy they required. So their situation is much like the other customer who needed to move incorrectly digitized features to a good location, to a more accurate location. So they're using it to move their water valves, their storm drains, their manholes, and their hydrants to their correct location. They're using that information, of course, to update their GIS so their features are properly located. Now, they happen to be using a Portland real-time base station. You folks know that GNSS stands for a Global Navigation Satellite System. So in this case, the base station is located at the Portland Airport, which is only 15 miles away from the city of Lake Oswego. They are connecting to the single base, receiving real-time corrections to 1 to 3 centimeters. And we'll talk about this in just a moment, but the level of accuracy that you can obtain is going to have a direct result according to how far away you are from a single base if you're using a single base solution. So we'll talk about that in just a moment. But they're able to get excellent accuracy. Their particular project required better than 4 inches. So rather than buying a decimeter unit, which would have provided 4 inches best case scenario, they decided to get something a little more accurate than they needed to make sure they were achieving their required accuracy. And they also saved a tremendous amount of money, on the order of about $9,000 over purchasing a survey system. So here's a graphic that sort of shows you the importance and some of the restrictions of what we call a single base solution. When you're using a single base station, obviously you're connected wirelessly to that base station, but it's important that both the base station antenna and your antenna are seeing the same satellites, of course. And because there is a distance restriction in this scenario, obviously they are because they're fairly close together. The base station sends the information to the receiver. the receiver compares that location to the known coordinate that the base station is occupying. That information is then broadcast to a radio, in this case a cell tower. The cell tower sends the data over to the rover, and it immediately and instantly applies corrections to your position in the field. And so this is what allows you to get that super accuracy. However, there is a linear equation that affects all GPS corrections, and that equation says that for every kilometer between the base and the rover, you're potentially adding up to 1 millimeter of horizontal error. So what this means is, potentially, if you were 10 kilometers away from a base, which is only 6.2 miles, you could actually be getting a centimeter of error already. But in this particular case, Trimble says that we can be 20 kilometers away, which is about 12.5 miles, and we can still maintain 1 centimeter accuracy. Okay, so here's what a multiple base solution looks like, or what we call a VRS. A VRS is a virtual reference station, and in the state of Washington, as an example, there are 105 base stations placed throughout the state and slightly outside the state boundaries, and all of them are sending their data directly to a single computer. Now, in the state of Washington, this computer happens to be located in Seattle. It's managed by Seattle Public Utilities. When you're in the field and you're connected to the internet, typically through a cellular modem, you have to log into the system and tell the computer where you're located. So you send a raw position back to this computer via the internet. The computer is receiving a position from you that's only good to about 15 to 20 feet because you're sending a raw GPS location to that PC. So the computer says, oh, I see where you are. You're right about here. Now, because you know that there's a baseline error, and because you now know that there's 1 millimeter of error for every kilometer of distance between the base and the rover, you can tell that if the base station is virtually 20 feet away from you, you're going to basically have 0 error because of how you're receiving the corrections. So a custom correction file is sent to the user, and it's able to determine where you are to an extremely high degree of consistent accuracy. Now, you can imagine that a multiple base solution is more consistent and more accurate than a single base solution because it doesn't matter how far away you are from any individual base station. It only requires that you are somewhere geographically inside that base station network. So in the state of Washington, where you have base stations everywhere, 105 of them to be exact, anywhere in the state of Washington, you can obtain 1 centimeter of accuracy with this system, providing you can get to the internet. So another way to get corrections would be Trimble's new RTX service. RTX just stands for real-time corrections. And it was introduced back in January of 2015, so it's only been around for mapping products for just a few months. It is a subscription service, and you can receive these corrections either directly from a satellite, if your GPS receiver has satellite capabilities, or through a cellular modem. In this particular case, the Trimble Geo 7X would be receiving the corrections through a cellular modem. You can see the difference in prices. These are annual fees to receive anywhere from 4 centimeters, which is just slightly over an inch, to 30 centimeters to 50 centimeters. And we do recommend that you get the right correction service for the level of accuracy that your system is capable of. You'll notice there is not a 1 centimeter solution, but in this particular case, it's a 4 centimeter solution. So let me ask you our second polling question. This particular question says, if I used a 1 centimeter mapping system, I would what? So when you see those choices coming up on the screen, just take a look at them, take your time, and select an answer. So it looks like everybody who's attended would be relying 50% on post-processed corrections, and 50% on real-time corrections via VRS, which is great. By the way, the state of Oregon has a VRS, the state of Washington has a VRS, and there probably are 12 to 13 other states in the country that do have this infrastructure in place. And that's really why the Trimble RTX service can be an option for some folks if you're in the middle of Alaska or the middle of Montana, and there happens to be a cell tower accessible. You can still get corrections even though the VRS infrastructure may not exist where you live. So thanks for answering that poll. Let me close that, and we will move on to the next slide. So this is something very important. We're going to get 1 centimeter of accuracy. Well, the Geo 7X is a carrier phase receiver. And of course what that means is that your receiver is counting how many carrier wavelengths there are between all the satellites in view and your antenna. And when that count is interrupted by trees, by buildings, by other obstructions, the counting has to start all over again. So what that basically means to us users is that it's virtually impossible to get 1 centimeter of accuracy under tree canopy. However, you can do pretty well. You can probably get 4 to 5 inches, but to get a centimeter is pretty difficult. So you do have to have a decent view of the sky, and you must maintain what we call carrier lock as consistently as possible. And carrier lock simply means you're allowing your antenna to maintain contact with a physical view to the satellites. You do have to have the Zephyr Model 2 antenna, which of course comes with the kit. That's a survey-grade antenna. And we do recommend a 2 to 4 minute observation time minimum on the first point. And this gives the receiver a chance to complete that count so that your accuracy can get down to the desired accuracy. Now, this is much more critical if you're post-processing. If you're getting real-time corrections, it typically takes just a few seconds for you to be able to confirm that you are, in fact, getting 1 centimeter. So keep in mind, this is one of the myths about GPS. I can buy this system, I can go into the woods, and I can get 1 centimeter. No, you can't do that. So let's talk about software solutions. Well, this is pretty easy. The only software data collection program you can use is the TerraSync Centimeter Edition. This particular hardware is not supported by ArcPad and Trimble Positions. It's not supported by ArcGIS Mobile and Trimble Positions. It's only supported by TerraSync Centimeter Edition. So this is the software that you'll use in order to get that level of accuracy. Horizontal and vertical, this always comes up, of course. TerraSync software uses a geoid model. A geoid model is basically a model of the Earth based on gravity readings. The current model is basically called geoid 12A CONUS, and CONUS stands for continental U.S. There's also some geoid models for Alaska and Hawaii and other parts of the world, obviously. This geoid model closely mimics mean sea level, and that's what enables TerraSync to convert a height above ellipsoid, which is how GPS collects its position, over to a mean sea level elevation. Here's a quick chart about the GNSS accuracy. Once again, it shows if you're using the internal antenna, you get 3 to 4 centimeters. If you're using a less expensive tornado antenna, you get 2.5 to 3 centimeters. If you're using the Zephyr Model 2 antenna, which once again comes with this centimeter kit, then you're able to achieve 1 centimeter horizontal and 1.5 centimeters vertical, and that's the ideal level of accuracy. So our last polling question, we're almost done here. Last polling question is, choosing or obtaining 1 centimeter of accuracy would allow me to do what? So just take your time and answer those questions. So yeah, improve the position accuracy of existing data, and of course get much better elevations, which is really a critical point for many people. And most of us remember that, you know, elevation has typically been the worst component of a three-dimensional position. And because the new units have a built-in electronic barometer, which in concert with the geoid model that now resides in TerraSync, is able to create what Trimble calls altitude-constrained positioning, which basically means you're getting almost the same vertical accuracy that you're able to obtain horizontally. So thanks for taking a look at that poll. The last thing I wanted to show you before we open this up for questions was this new receiver. This has nothing to do with the centimeter kit, but this product was released just about 2.5 weeks ago, and I just wanted everybody to be aware of it. It's called the R1 receiver. You can tell that it's about the size of a deck of playing cards. It provides sub-meter accuracy. It picks up all 4 constellations of satellites, the U.S., the Russian, the European, and the Chinese satellites. It can receive SPAS corrections. It can receive VRS corrections, which of course is VRS or single base. It also can be subscribed to Trimble's new RTX correction service. It does have Bluetooth. It does have a 10-hour battery. And the thing that people like about it most is it will talk to virtually any device. So for the first time, Trimble has actually released a product that will talk to an Apple iPhone, to an iPad, to a Samsung phone, to a Galaxy tablet, to a Windows mobile device. It basically is authorized by these various companies to talk to their devices. So we have a lot of requests for people that want to use their phones or their iPads to go collect data, but they are not willing to live with the 15 to 30 feet of error that that device can produce. So if you want to use your phone or your tablet, you can now actually take advantage of this particular product, go out there and get sub-meter accuracy, and still use your own device to do the actual data collection, just to give you an idea. So I think I was having some issues in the beginning of this webinar hearing you guys. So I'm going to make sure that everybody is unmuted and just open this up for questions if you happen to have any questions. So I guess you can probably hear my voice. I have not been able to hear your voices yet. So I'm going to unmute everyone and see if you can ask me. If for some reason I can't make audio contact with you, then please make sure to contact me by telephone or email after this webinar, and I'll put my contact information up here. My name is Jim Lom. I'm with Electronic Data Solutions, and my email address is very simple, jim@electdata.com. And for those of you in different parts of the country, we have people that work in these other areas, and I'll be happy to refer you to those guys because they may be your salesperson or your local representative. So since I can't hear you guys, I apologize. We're just going to end the webinar now. And just take note of my phone number and email address. I'll be happy to help you any way I can. And thanks very much for attending this webinar. It is recorded, so if you want to refer one of your colleagues to this recording, it should be available within 1 to 2 days. I appreciate your attendance, and thanks very much.